right, the biggest one I saw was Mersenne primes. You got to a place, so if you used ChatGPT, it didn't give you enough detail, because the big part of what you have is that if you have n is composite, that you can write this as a times b, where a and b are both bigger than 1. That's the most important part, that those two things have to be bigger than 1. If they're not bigger than 1, then it's possible that you have a prime. So that's the issue. So you have, once you have that, and you do, the question is, why would ChatGPT tell you to do this? Why not just say 2 to the n minus 1? You get what I'm saying? It asked you to do this before you factor. Why would it put 2 to the a here? Why didn't it just take 2 to the n minus 1 and factor that?
Could 2 to the a be like x and then...
Yes, that's what's going to happen. But why did it have to do this? It didn't explain that to you. Sometimes there's issues with ChatGPT, especially for pure math. I can get it to give you wrong answers a lot in this class and topology. So you have to kind of look at that carefully. What do you think could be? Why do you think it's doing this?
I mean, it's pulling probably from like Wikipedia or other things. It's just, I guess literally.
Even Wikipedia left off the details. Actually,
yeah,
somebody used Wikipedia, so
it's doing it because it's pulling that off Wikipedia.
maybe it gave more detail than that was on Wikipedia though. Okay. So it's pulling some more stuff from that.
Man, it's a probability algorithm. Like, what's the likelihood, or what's the next best word to put out?
This is correct though, but there's a reason. You kind of have to understand the reason of why it's telling you to do this. Why can't you just do this and factor this out?
Is the factor identity?
You can use the factor identity towards this too, right? The issue is, the problem actually is that if you want to use the formula that, if you set this to be x, if you want to use this formula that Dr. Sarajin showed you in class and proved for you in class, the reason this works is because x has to be bigger than 1 for this to make sense. And this 2 to the a, because a is bigger than 1, this 2 to the a is bigger than 1. And then you put it into 2 chunks. This is your s and this is your t. And that will prove that this guy is composite because s is bigger than 1 and t is bigger than 1. I'm going to let you prove why s is bigger than 1 and t is bigger than 1, but you have to explain why that's true. Because if any one of them is 1, then the other one's prime. It didn't work, right? So it's the fact that these are bigger than 1. It left out that huge detail. Does that make sense? So it's interesting looking at ChatGPT and how the different classes are using it. I think MA 103 is a complete success. 104 will be a complete success because there's lots of stuff on the internet with calculus. Like calculus has been there since Newton. So, but for pure math classes, you have to really sniff check it and ask yourself, well, why is it doing the things it's doing? I'm not prohibiting using ChatGPT because I think this is the world we live in, and you have to learn how to use it properly. I use it a lot for writing difficult conversations. I write into it exactly what I think, with curse words and everything. Like, I hate you, I don't want you to do this ever again, I wish you would never talk to me again, etc., etc., etc. Make that polite and professional, and draft me an email. And it will. It'll make it really polite. And then sometimes I'll ask it, I want it polite and professional, but stern. And then it'll give me something. So I have to go sniff check and look at it and go, I need it to be more stern. So it'll do that for you. So it's really, really good at doing these like counseling type emails that you'd have to send out. And it's very therapeutic because I get to say exactly what I feel.
Man, what does the edge of learning look like in math right now? What would we have to start working on for like at what point do you kind of hit the edge of learning where the internet just is not helpful at all?
I think for pure math, it's not. It can be used as a resource, just like Wikipedia. If you go to Wikipedia, it doesn't give you the full thing. Like I remember my cadets in abstract algebra saying, "Ma'am, this was not on Wikipedia. The problem you came." Okay, now you can contribute to that and put that there. that's your final. Put that there. I think for pure mathematics, there's always, it's just too big of a field to actually put in, too hard. There's not enough of people in there to actually put this stuff. I think for coding, it's amazing. ChatGPT has changed the world of coding. Even the best coders here use ChatGPT to get code snipped down. So. You always need the human mind, though, to do those sniff checks. You know, think about NLP. Does anybody work on NLP here for their capstone? Or you can write code to take that free text and distill it and understand. But a human has to go in there and say, does this make sense? What's in these brackets? What am I looking at? So I don't think you need to fully take the human out of the loop. I've been asked that before, like, can you take the human out of the loop and just automate everything so someone can push a button? Bad idea. That's a terrible idea, especially in medicine. You always need someone to go back and say, does this make sense? All right, so does that help with this problem? Any more detail you need? All right, so that's the detail I asked you for. And then I think, is there another question that I had? The 2n minus 1 and 3n, the 2n plus 1 and 3n plus 1. I asked some of you to revise that because sometimes the proofs are clunky. So there's a slick way to do that. I think the slickest way is with adding the two equations. If you add them, and you can get everything to disappear, and you'll get d times something is equal to 1, so d has to be 1. That's the slickest way, I think, to do it. So I put those, I think that's pretty self-explanatory. I did print out your next homework. We'll actually look at that at the end of class so that I give you, I think it's harder because it's just harder to understand the material I'm giving you right now. So I want to kind of go over that a little bit in class. All right, so in class, I gave you something the other day to play with, and I think it was really hard because the property 3 ended up not being true. So I'm going to give you an example of a sigma algebra, and today I'm just going to do this on the board because I'm too lazy to go put everything together. So what if I have a potential sigma algebra, because I have to prove it. So my omega is going to be the natural numbers again, and f is going to be sets where either countable or 2, the complement is countable. So similar to the one I gave you before. And this is not going to have the even odd problem, right? Because if A is the set of evens, it's countable. It's countably infinite. So I check off the blocks. 1 is n in there. The whole space. Alice, why do you think so? Somebody famous came to class and told you what about n? It's countable, right? Dr. Calkin? It's countable by default. Is empty set in there? Empty set by itself is not countable, but the complement of the empty set is the whole thing. Property 2. Let A belong to the F. Then I need to show what? What's the second property of sigma algebras?
Complement.
The complement's in there. Right. But there's two possibilities for A. Case 1, A is countable. Then I'm done. Well, actually I'm not. The only possibilities are that you get the whole thing again, because the original thing was empty set, or it's going to be a countable set, because you got something like the evens, well, the complement would be then the odds, or the complement could be finite. How could the complement be finite? How can that happen?
I think it's all natural numbers except for
Yeah, poke a couple holes in there. So like maybe start with 3 to infinity, and then I have left out 1 and 2. Then the complement's going to be 1 and 2, so the complement could be finite. So the only case I have to worry about is this one. So B belongs to there. Actually, I could have just used this one for all of them, but it's nice to think about what those sets could look like. So I'm thinking it over. How can B get into that set? Either itself is countable or its complement is countable.
So basically you're saying if A is in the set and A is finite, it got into the set because the complement of A is finite.
Well, yeah, I started off with this, right?
Right.
So if B, so that's why I was saying I could have actually used this for the whole set of arguments, right? Because I started off with A is countable. So if the complement of B is not countable, well, I can just tell you that B itself, the complement of B is this, right? Either or. Either can be that the original set was countable or the complement was countable. So if I set B to be the complement of A, then when I complement both sides, I get something that is countable.
Gotcha.
Bookkeeping. Case 2, complement of A is countable. Well, then I'm done. Does everybody understand? Carly?
I don't, like,
How does a set get in here? Either A is countable or the complement of A is countable.
well, like in case 1 we say A is countable.
Right. So if A is
but we're not
countable,
done, but
then the complement, then I can look at let B be the complement of A. Well, then if B is the complement of A, then the complement of B is countable. So the complement of B is in here, which means that the complement of A has to be in there.
Wait, so, but why for case 1 do we say like A is countable but not be done, but then for case 2 we say the complement of A is countable and then we're done?
Because we're trying to show the complement belongs to there. So this part is if A belongs to F, show A complement belongs to F.
Oh, okay. Okay.
Those proofwriting guide things of writing down what it is you have to show, It's not for the easy things, it's actually when it gets more complicated to keep your head straight. Last one? Last one's always the hardest. Let A1 through blah, blah, blah belong to F. I need to show the union of I equals 1 to infinity of AI belongs to F. That's true, right? If I just have one AI that's countable, then the union of all the AIs is also countable. Because AI belongs to that union. I shouldn't have used the I's here again. How about K's? This union is bigger than all of any one of these. If one of them is already countable, then the whole union is going to be countable. Good? Make sense? If you don't understand, say so. Like it's not easy to do this. If you want a concrete example, let's suppose that all of these guys inside here were finite except for one, and one of them happened to be the evens. Well, then you're going to be having the evens plus some more when you union up other things. So this one's going to be larger than just the evens if just one of them was evens. Make sense?
What does that say, the Parger set? Then
Say again?
what does it say when you're pointing to A sub k? The par set?
This union is going to be a larger set than just one
Larger
of
set.
them,
Okay, I
right?
didn't know
Because union is making them bigger.
I just know what it said. It looked like a P. Yeah, so I didn't know what it said.
All right. What's the worst case scenario for all of these? Like if one of them is, at least one of them is countable. Let's go to the other case. None of them are countable. What does that mean if none of them are countable?
Countably infinitely.
None are countable.
Countably infinitive. They're not countably infinitive.
Right, so like each one of them is finite, right? But then if I union them, there's two possibilities. That they gave you something, like I built up the evens the other day, I think. If I just, I could just keep, or I think the easiest thing is you could take the union So you can take something like this. They are just up to the ith number. And then, so each one of them is finite, but when you union them up, you're going to get the countable set. Or the union of the whole thing somehow ended up being finite. If the union of the whole thing ended up being finite, it's like I've taken the natural numbers and just punched out a bunch of holes. A finite number of holes. Whatever's left over. It's kind of like what that guy said on the proof. You haven't got very far, have you? If you take out a bunch of finite things out of the natural numbers, there's still an infinite number left over.
So for this example, you're saying like A1 would be the set 1, A2 would be the set 1, 2, A6.
Yes.
Okay.
Right. So that if you union them all up, you get.
The infinity.
Yep.
That makes sense.
I can't even imagine what example I can make where I make this, but let's say worst case scenario is union of these AIs is finite. That's the worst case scenario. But then the complement has to be has to be, because I've only punched out. What you've done is the complement would be, let's say a hole here, a hole somewhere else, dot, 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 but I have just a final hole. There's not going to be more. So what's left over is going to be everything else, and everything else has got to be infinite, because I've only punched out a finite number of things. You can just do that yourself, right? Take a number line and just punch out a few holes. Whatever's left on that number line is going to be infinite. Agree?
And can you write the complement of that set as the natural numbers? Well, what's it called with the
De Morgan, you mean?
No, it's not De Morgan. It's with like.
Oh yeah, you could do that. You could do it symbolically. There's actually someone in topology that always asks for that. So you could say, the union of this, if you want to do it symbolically, just ended up being a bunch of finite set of numbers. Then the complement of that is equal to the natural numbers minus just those holes you punched out.
Gotcha.
Yeah.
What is the name of the backslash? It's like the relative complement.
I think that's what you guys are using. I don't use that. I just use n without. Yeah.
I got that on the internet from midterm. Just like the name backslash.
I thought maybe you guys got it from discrete math.
I heard it from Cooper.
I heard it from John. Showing us face.
Thanks, John.
But sometimes we suppress it and we just say or complement of, because it's known that you're working on the natural numbers. So it's just the complement of that set inside the natural numbers. All right, I'm gonna blow your minds now. We're gonna do if I haven't already. So there's these sets that we work with, and what I want to build you up to is something called the Lebesgue measure, which my topology class is dying because they would love to learn what a Lebesgue measure is. They usually teach it in a undergrad real analysis course, if you're crazy, or you teach it in a graduate course. And so I'm going to take my attempt to show you these things in this course in 3 lectures. I think the reason that this is considered higher level, because each chunk of what you're learning is not hard. You just have to think about it differently than you have ever thought in your life. That's because that's such a shakeup of how you thought. I think that's the issue. But a European once told me, because I used to say, you guys have it easier. You guys learn all this pure mathematics as an undergrad, and you're all ready to do it here. And he goes, we cried earlier than you. You're crying now. There's still a month of crying. Get over it. So I think it's just hard for people to think like this. once you can think like this, no one can take that away from you. You can always be able to think like this. It distinguishes you from other disciplines because you're able to think like this. All right, there's these things called Borel sets, and the idea is the following. So I have the real numbers. That's my omega. That contains open intervals. So you had something like this before. Everybody took linear algebra. You had something like this before. It was called span. So you were given a couple vectors, and you're asked what ingredients they didn't make you think of it this way, but really what you're doing is asking yourself, let's say I have the span of two vectors, 1, 1, 0 and 0, 0, 1. What ingredients would I have to add in there to force that thing to be a vector space? So I can do linear algebra on top of it. So you would add things. Well, to be a vector space, it has to be closed under addition. So then the sum of those two vectors would have to be in there. It also has to be closed under scalar multiplication. So any scalar multiple of any combination of those sums will also have to be in there. And then you didn't probably think of it like that. They probably just told you a definition of a subspace or a span is that you would have to have all linear combinations of those vectors. They probably just told you. But that's what that is. The span of a set of vectors is the minimal vector space that you can generate from those two vectors as a seed, or those three vectors as a seed. So we do this a lot in math. We ask ourselves, like, I don't have a field. What ingredients would I have to put in here? That's for you. You did that. Did you do field extensions?
Yes.
Yeah, that's what a field extension is. I don't have a field. What ingredients would I have to put in this set so that I get it to be a field? So this concept's not foreign. If you continue on in math, you'll see this again. You go, aha, I remember Dr. Thomas talking about this.
Isabella's not here.
I'm just going to call it B. Open intervals have to be in there. I don't want to give you one that I gave you already. Okay, so let me think. So any open interval has to be in here. And I've got these three properties of sigma algebra.
Man, what was the first one in the where it has to be in?
Omega has to be in there.
In there.
Right? These are just the sigma algebras definition. So I'm going to play with this. Let's just take one open interval. Pick your favorite open interval.
0.
0 to 1. All right, let's draw that on the board. I'm on the reals. Here's my real number line. My daughter told me to stop gifting little kids number lines. Like I like to give as a gift for a birthday party a number line that rolls out onto the floor that they can walk across. And she's like, they're gonna hate you. Don't give them that. I also got them Bayesian probability for babies. These are great gifts, I think. Forget Legos and Barbie dolls. You get a roll out number line. So this is my real number line. My daughter says, I love the number line. Best thing you ever learned, ever, is the number line.
Yeah.
Think about it. You start out with just the counting numbers, that's part of the number line. And then you extend it to negative numbers, that's the integers, that's part of the number line. And then you put in some stuff in between all those numbers, that's the rationals. And then you say, okay, there's like gaps in here, there's limits that are not in here. So they close them all up. That's all from K through 12, that's your education. And then one day you say, hey, I can't solve x squared plus 1 equals 0 on this number line. So you make the complex plane. There you go. You got college covered too. All on the number line.
I had Miss Gale. Her entire job was for kindergartners at my school to go sit in front of her, and she would just listen to how high we could count. She did that all day, every day, for every kindergartner in the school. And some kids would get to like 8 million, 9 million. Like 8 million. She just had to sit there and listen.
No wonder kids think that that's what I do here, right? I'm just adding really huge numbers together. All right, so we're going to take 0, 1.
Of course I thought.
That's that. So let's look at properties. 0, 1's got to be in there because that's my seed. That's how I seed it up. So if I want to write Borel sets, I know Borel sets have to have this in there. I just don't know what else is in there. There's a lot of stuff in there, right? So if I go to this property, what does the complement look like of 0, 1?
All the normals without 0, 1.
But that whole interval, we're on R now, we're not on N. Take a different color. So I shade through everything that's not covered by that blue line. So it would be this. Oh, this is work. It'd be this. That's the complement. How do you write that down? You don't. That's too lazy. I hear minus infinity to what?
0.
Included or not?
No.
And then
Yeah.
so that new set, by property number 2, that new set is inside there.
So the complement is in because the complement.
Because that's the definition of sigma algebra, right? So I know that's in there. It's just like if I had 1, 1, 0 and 0, 0, 1, 0, 0 in a span, I know that the sum of those two things is in there. So I know at least one new vector that's in there. It's the same idea. So I want to see if you guys can generate somehow some of the other stuff in here.
So that's the complement of B.
No, I complement of B is empty set because no, complement of B I have no idea. Like we're not going to be able to create everything in there. It's a weird looking set.
So it's just the complement of our open.
Yeah, just one open interval. So I know now something new that's in there that hasn't, that is not an open interval. So the first question really is, are there only open intervals in here? Well, no. Now I have this. So this is hard. You're going to test your mind. See if you can find some other stuff that's in there. Go ahead.
Ma'am, if an open set is in B and the complement of that open set has to be in B with basic algebra, doesn't that also prove that all reals are in B?
Well, that's my question for you.
That's kind of
It's sort of like
That property tells you that R has to be in there, right? Like you already are given that this satisfies a sigma algebra because this is the seed. You're gonna put in open intervals in here. And then you're gonna see like, are other things in here? This already gives you, that property already gives you R is in there. R has to be in there. So I can manually put it in there. That's gotta be in there.
okay.
Right? That's the first question I ask you. But you can also generate it with open intervals if you want to. Take boards, work together. Don't work alone.
I think